My name is Berkehan Tatli. I'm a master's student from Technical University in Ankara under the supervision of Dr. Tuncay Yalçinkaya. Today I'll be talking about the initiation and propagation in dual phase steps through crystal plasticity and cohesion of frameworks. Here's my outline. First, I'll motivate my speak by introducing the dual phase steps and their failure mechanisms, and I'll talk about my aim of the study. And I'll show you our micromechanical modeling approach based on constitutive frameworks, failure analysis, finite element modeling, and parameter identification. And we'll show some numerical results based on our framework, and I will give a brief conclusion and discussion. Let's start with our introduction. Dual phase steel microstructure is composed of two phases. The ferrite phase is known as the soft phase, which gives ductility to the material, and the martensite phase is known as a hard phase that gives strength to the material. They are actually used mostly in automotive industry due to their various advantages, such as high tensile strength, good elongation and ductility properties, high strain hardening, and early yielding stage. But even though they have various advantages, of course, they also have some complicated issues because of their inhomogeneous microstructure, and their mechanical properties vary with the volume fraction of the martensite. So in order to have a deeper understanding on the mechanical response and the ductility to strength balance and optimize it, one needs to have a deeper understanding in the microstructure and the analysis of the microstructure. The dual phase steels have mainly three failure mechanisms. The first one is ferrite-ferrite decohesion, the second one is ferrite-martensite decohesion, and the third one is martensite cracking. In the literature, one can find that as the martensite volume fraction increases, the failure mechanism goes from the first one to third one. For example, for low volume fraction dual phase steels, you observe ferrite-ferrite decohesion, but as the volume fraction increases, the ferrite-martensite decohesion that leads to martensite cracking. So in our model, we aim to understand failure mechanisms by including the ferrite-martensite decohesion and martensite cracking at the microstructure scale. For this purpose, we implement the cohesive zone between the ferrite and martensite grains and ductile fraction model within the martensite grains. And we analyze some numerical examples by varying volume fractions and morphologies and orientation sets, and we discuss on them. These are our constitutive models. For martensite phase, we use J2 plasticity model directly taken from the literature. This model kept constant for all of our analysis, so this is the only one we use. But for ferrite phase, we use two approaches. One is for the inclusion problem that I told you about later. In the inclusion problem, we use J2 plasticity model, but in the polycrystal RV, cubic polycrystal RV model, we use the crystal plastic framework. Actually, the J2 ferrite phase model also is taken directly from the literature. Crystal plastic framework, as we all know from maybe that we work on that, is a local and rate-dependent model, and we have three different parameters for the hardening tube. This is our failure frameworks. As I mentioned, the failure frameworks consist of two different approaches. First one is based on the intergranular failure between the martensite and ferrite. This is the model that we implement between the intergranular failure. It is a mixed mode model. It's a potential base. We use 12 model elements. And for the martensite fracture, we use a ductile fracture model from BAO, and we directly take the model from the literature as well. These two also. These are our finite element models. As I mentioned, the left one is the polycrystal cubic RV that we try to investigate the response of the stress strain as we're varying the volume fraction and the morphologies. We try to investigate damage evolution between different morphologies and orientation sets, and we observe the crack paths between the, as I said, microstructural differences. For the inclusion problem, we use two J2 cases. One is for martensite, one is for ferrite. And we use this model to identify cohesive zone parameters and ferrite phase hardening parameters. This is our J2 flow curve. This is directly taken from the literature. Actually, this is an experiment, and these are the identified parameters for hardening for both phases. This paper also gives the hardening parameters for simulations. And the right one shows the calibrated ferrite phase curve that we implement in crystal plasticity. As I said, since we use J2 and crystal plastic for ferrite phase, to be consistent, we calibrate our the crystal plasticity curve to the J2 curve on the left, and you can see the calibrated parameters on the bottom. In order to identify the cohesive zone parameters, we use the relation between ultimate strength and hardness. There is a linear relation that can be applied to steels. So once you have the ratio of the hardness, as you can see, you have the ratio between interface and ferrite. Once you have the ratio between the hardness on the interface and the ferrite phase, you actually can identify the maximum interface stress on normal and tangential modes. So for that, we created a no hardness test model simulation, and we just we just read the values, and this is the ratio over time plot. The average value of the ratio was seen to be 1.67. So we just calculate our normal maximum traction value. It turns out to be 1,160 megapascals. We also compared our results with the literature. In the literature, they also use similar values. For example, here you can see 1,100 megapascals was selected in one paper. And in order to fix our traction in the tangential direction, we use another relation from the literature that says that 35% of the normal traction is equal to tangential traction, and it turns out to be 385 megapascals in our simulations. So once we fix the tangential and normal traction values, we try to fix our energy values and shape parameters for our cohesive zone model. For that, we did some trial and error simulations, and we found out that these are the sets should be used for the PPR. But once we try to fit our PPR parameters into the experimental data, this is the experimental data, you can see like 2015. Once we observed that without changing the hardening parameters for ferrite phase, you cannot fit data into the experimental data. Then we searched for it, and we learned that there is an effect called artificial compliance, which really affects this soft hardening phase on the stress-strain response. So actually we fit the PPR parameters and ferrite parameters all together. Then that means we change the ferrite hardening parameters as well. So in order to fit again the crystal plasticity parameters with the ferrite curves parameters, we again calibrated our model, and we just recalculated the parameters. And these are the calibrated, final calibrated data. As you can see, left one is J4, J2, and right one is for crystal plasticity. Then we start our numerical examples. In order to see the effect of the artificial compliance, as I mentioned, it's a huge effect on the hardening phase of the simulations. We started with the previous ferrite phase parameters. These are all crystal plasticity models. Ferrite phase is modeled with crystal plasticity. Martensite is always, as I said, modeled with J2 plasticity. For 50 grain models, as I said, we use the initial ferrite parameters. So you can see the deformed shapes and the stress-strain response on the screen. As you can see, there's an anisotropy. This is due to the low number of grains in the model. So in order to have an isotropic response, we need to have plus 200 grains roughly. So that's why the initial hardening phase is not match each other. This is the numerical examples. The stress-strain response of the four model that I showed you previous slide. As you can see, as the orientation set, by the way, orientation sets of each is different from each other. The only difference between these four models is the orientation sets. So as the orientation sets change, you can see that, for example, in this grain boundary, this is even dequiet, but this is still intact. The others also seen similar effects, but this is the most critical and explicit one, so I showed that one. We understand from here that the changing the orientation sets really changes the stress-strain response, the breaking paths, and damage evolution, as I showed you right now. For example, this is the damage evolution of the same four specimens. As you can see, near the grain boundaries where the two martensite grains coalescence, you can observe a huge damage accumulation, whereas the other parts are damage-free. And as the literature suggests, where the martensite and ferrite equalization starts, there should be a martensite cracking also occurring, as I mentioned previously. So this also this also coincides with the literature data and literature suggestions. So this similar study also performed on the 37 body fraction case. As you can see, due to the anisotropy, the initial hardening phases do not match very well, but we try to understand what differs between orientation sets, morphologies, and volume fractions. And as we continue, also you can see the stress strain response of three specimens. Here, the striking difference is also more clear than the previous one. For example, if you can see this intergranular failure and this failure, this is still intact and nothing has occurred in terms of failure, but this is already gone failed. We also observed that as the volume fraction increases, this is the damage evolution graph again. As the volume fraction increases, this means the number of Martensite grains also increases. As Martensite grains increases, there is more grains to take strength in the material. So we observed less damage for the high volume fraction, which was very intuitive, I guess. Then we did some cylindrical specimen examples. This cylindrical specimen was applied to a boundary condition that is fixed on the one end and applied a boundary condition for uniaxial displacement. You can say the number of grains increases and isotropy decreases as the initial phases are more close to each other. Again, we observe some similar results. For example, the interface between the first and third one. You can see that this is a bit equate, but this first one already gone too low. The damage evolution, for example, for these examples are like that. In the damage evolution, in these examples, we do not observe very high damage values, but still, for the first example, you can see that the damage on the between the Martensite grains actually gone to the value of 1, which means the Martensite cracking has occurred. And this is a similar example, actually, the specimen. Again, we try to show you that the stress strain response and the damage accumulation actually differs based on morphologies and orientation sets. This is for the same volume fraction. Also the damage evolution. And finally, we try to verify our models with the experimental data. So we used our calibrated crystal plastic parameters. As I said, to see the artificial compliance effect, we did not use the calibrated parameters, but in this example, we 280 grains to have isotropy. We use the calibrated crystal plastic parameters, then we try to figure out how the cohesion zone elements actually affect the total response without and without. So the blue curve is actually based on the experiment from Lay. As you can see, especially for the initial stage for hardening, we closely match, and that agrees our model seems to work and has a hoping results. This is the stress strain response in order to compare the effects of the different morphologies. Again, you cannot see clearly, I guess, but there is still some difference in the stress strain response of Martensite grain, for example, in here. And this is a damage evolution. You see a, sorry for the slow video, by the way, this is unexpected. In order to, there will be a damage accumulation here. So still, this is a similar place where the Martensite ferrite decohesion occurs, and this decohesion yields to a Martensite cracking as the damage runs to 1. But in the other case, the other example, due to the different orientation sets, you cannot have a Martensite cracking with this configuration. All in all, to conclude our work, we observed that capturing the failure mechanisms at the microscale in two-phase steels is a challenging process. You need to tune everything with the experimental data, with your own data. But still, the combination of physics-based plasticity frameworks with right failure models, you can capture the realistic results as I showed you for the 280 grades. These kind of plasticity and failure model frameworks can be employed together to understand microstructure better and design for anything for requiring understanding of the microstructures. Still, in the current work, the modeling of intergranular failure of ferrite did not be considered, but still it can be included with the same approaches. And phase field models also employ these models, can be employed models as well. Thank you very much for your patience and listening. Are there any questions?
So you use the J2 model for ferrite and the crystal plasticity for Martensite, or the other way around, right?
No, we use J2 model for the inclusion RV case to fit the parameters to have faster solutions. I mean, if you use crystal plastic models for Ferrari for every tuning process, the simulation time is actually about 12 hours or 13 hours. In order to fit the parameters, we just created a two-grain inclusion RV to mimic the actual results. Then we get the parameter fits in that model, but then we fit our crystal plastic parameters to J2 parameters obtained in the curve. Then with that crystal plastic parameters, we actually simulated these 50 grains and 280 grains models.
Thanks for the interesting talk. My question is, how did you, well, I understand from the volume fraction of martensite and ferrite, but how did you determine the exact morphology of the microstructure in your examples?
Actually, we created it from open source code Never, the microstructures. Then we just changed the grains by hand. So the only change is in the morphology, if you ask that question. So the tessellation is the same, but we assign the grains to change the morphology a bit or more a bit.
Thank you for your interesting talk. I learned quite a lot. Do I understand correctly that you used the bow Wierzbicki?
Yeah.
I'd like to point out that that's been superseded a couple of times by the Wierzbicki and then the Hosford Coulomb. So you might consider using those. But also, I think I'm not sure that those are necessarily appropriate for this condition, because I think that they're like a continuum homogenization of the things that you're describing here.
But the thing is that we looked for the Bau's paper, and Bau says that for the low strain of martensite, I think it was 2%, if I remember correctly, the model can be worked on any other models, so we just choose that one and implement. But thanks for your suggestion. So we can correct and improve the models. That's what we are doing actually right now, but this is for the conference. So we try to improve the model at the same time.
If you want a more up-to-date, consider the modified Coulomb or the Hosford Coulomb. Yeah.
Thanks very much.
Any other questions? So, thanks, speaker.